Yes, I will give a presentation titled Simultaneous Observation of Faint Meteors with Meteor Radar and Tomo-e Gozen Schmidt Telescope. The origin of meteors is thought to be small bodies. When this dust enters Earth's atmosphere, it emits light and is called meteor. Comets, in particular, are generally known to be the origin of meteor showers, because they emit dust and create dust trails. There are two main types of meteor observation methods: radio observation and optical observation. Radio observation is to emit radio waves into the plasma space around the meteor and observe the echo. On the other hand, optical observation is to observe light produced by meteor by overlapping the observation range. The same meteor can be observed. In fact, simultaneous observation of meteor has been done using Tomo-e Gozen and Meteor radar. Meteor radar is a high-power large aperture radar located in Japan. Meteor radar observes head-to-echo plasma of a meteoroid and obtains orbit of the meteor by assuming tracking meteoroid. On the other hand, Tomo-e Gozen is a high-sensitive, high-field of view camera in Japan that consists of 84 CMOS sensors. It has a frame rate of 2 FPS, and when a meteor is observed, it is detected as a straight line, from which the brightness can be calculated. So far, about 10 magnitude of faint meteor have been observed simultaneously, and their orbit and brightness have been calculated. It can contribute to the part of the mission known as Destiny Plus because it can observe faint meteors. Destiny Plus, it is a flyby observation mission planned by JAXA ISAS, where Phaeton is the target object. Phaeton is an active asteroid believed to be in the process of transition from comet to an asteroid. Phaeton is thought to be the parent body of the Gemini's meteor shower. In Destiny Plus, the characteristic of the dust emitted from Phaeton will be investigated by flyby observation within 500 kilometers of Phaeton using dust analyzer. In this case, how much dust can be acquired by the dust analyzer will be important to estimate the payload. Therefore, we would like to continue to contribute to Destiny Plus by obtaining the mass distribution of the faint Gemini meteor shower, though through simultaneous observation of meteor using Tomo-e Gozen and Meteor radar. Actually, the mass index, which is an index of mass distribution, is calculated by using Tomo-e Gozen and MU. This paper, simultaneous observation, was conducted with Tomo-e Gozen and MU radar, targeting sporadic meteors. This figure shows the relationship between rebound magnitude and RCS of simultaneous events. RCS is a parameter of reflector's ability to reflect radio waves. The larger this value is, higher the reflective capability. Then you will get the equation of the relationship between RCS and V magnitude. This formula is very useful for converting RCS to magnitude for MU radar without simultaneous observations. In fact, this paper converts the RCS observed by MU radar to magnitude, which has not been observed simultaneously in the past. In, uh, in this paper, the mass index was calculated using 100,000 sporadic meteor observed by MU radar only. The RCS and magnitude equation obtained earlier is used in the calculating mass. First, the RCS obtained by MU radar is converted to magnitude, and then magnitude is converted to mass to calculate the mass index. Thus, RCS is an important parameter for the calculation of the mass, but there is uncertainty in the calculated masses due to effects such as luminous efficiency and fragmentation. The James meteor shower, which is the target of this study, is thought to be depleted in sodium from past observations. This diagram is a triangular diagram showing the ratio of iron and magnesium and sodium. The Gemini meteor shower observed in 2018, 2070 is plotted into figure, and it can be seen that the Gemini meteor shower less sodium. And closer to the axis, the less sodium is presented. This figure shows the ease of ionization, and the closer it is to zero, the easier it is to ionize. Also, sodium is easily ionized and electrons are produced with less energy. Therefore, the tendency of RCS that can be obtained by observing the Gemini may be different from that of typical meteors. Therefore, in order to investigate the effect of comparison, we are conducting spectroscopic observations in addition to simultaneous observation with MU radar and Tomo-e Gozen. In this 2020 observation conducted this time, the Gemini meteor shower was targeted. A total of 60 hours of simultaneous observation were made over 2 days. The number of meteors events is estimated from the number of meteor events at simultaneous observation in the past. Because MU radar data is preliminary and is still in the process of analysis, the location of the Tomo-e Gozen and MU is shown here on the map of Japan. The number of Tomo-e Gozen sensors used in 40 sensors, and that FOV. In addition, the 2020 simultaneous observations were made by adding spectroscopic observation to just described. Simultaneous observation using 3 instruments lasted 2.5 hours. The 48 meteors were detected in spectroscopic observation only. There were 2 simultaneous observations, spectroscopic and Tomo-e Gozen. Next, I will briefly introduce the analysis flow of Tomo-e Gozen and MU radar. As for Tomo-e Gozen, the author code reduces the number of frames where noise and satellite are detected. In this case, the number of data after the reduction reached 100,000 frames. And however, it should be noted that there is noise that could not be removed, and overlapping of meteor being detected by multiple Tomo-e Gozen sensors. In the MU radar data, the meteor position as seen from MU radar converts to Meteor position as seen from Tomo-e Gozen. There were 6739 events in this emulator observation, but it should be noted that this is preliminary data. In this analysis, by using the time, we obtained the simultaneous meteor of 2027. From here, we can use some similarity of the trajectory to determine whether it is a simultaneous meteor or not. Therefore, for Tomo-e Gozen data, we use half transformer, which is a method to detect straight lines to extract the location of meteor trace. The emulator calculates the position of the meteor trajectory as seen from Tomo-e. Finally, the same meteor is determined based on the similarity of the trajectory. Subsequent analysis will determine the magnitude and mass of the same meteor. Now we are analyzing this stage. The following section describes the process of calculating the magnitude from meteor flux. This formula was used to obtain the flux of meteor. Exposure time indicates the exposure time of Tomo-e Gozen. 0.5 seconds is used in this analysis. Omega is angular velocity of the emitted meteor shower as seen from Tomo-e Gozen. This value shows how many peak. This value shows viewing angle per pixel, and this dotted line shows how many pixels of meteor will pass during the exposure time. The meteor is observed as straight because the exposure time. From this trajectory, the brightness distribution is obtained in the vertical directions. And the sum of the brightness distribution is obtained as the line intensity. It gets the flux meteor. Next, I will take calculating the magnitude of meteor by comparing its flux with that of stars. This slide shows the process of converting meteor flux to magnitude. First, the flux of meteor observed by Tomo-e Gozen was converted to G magnitude by using magnitude of the stars observed by Gaia, because it was considered risky to convert meteor flux to V magnitude directly. Then, by comparing the G and V magnitude of same stars, we derived the formula for converting G to V magnitude. Using the formula, they convert the initially calculate G magnitude of the meteor to V magnitude. This is how the magnitude is calculated. However, the observed data is still being analyzed, so the magnitude has not yet been calculated. Next, let's talk about results. We will start by presenting the result of simultaneous of emulator and Tomo-e Gozen. Since we are currently in the process of analyzing the brightness of meteors, the equation was used to convert the RCS to magnitude. This equation shows that the larger the RCS, the brighter the magnitude. This figure is luminosity function of the Japanese sporadic meteor shower. And the RCS of Meteor observed by 2020 was used. Note that the meteors other than the Gemini's meteor shower may be included. This figure is a luminosity function of Gemini's meteor shower. In the case of sporadic meteor, it can be seen that they don't lie on the straight line of the linear relationship due to the large cumulative number of bright meteors. The brighter the meteor, the higher the RCS, which indicates the higher ability of the meteor to reflect radio waves. In other words, the high RCS means that meteors, high RCS means that meteors in the direction where radar sensitivity is low are reflected. It is thought that the number of bright meteors increase due to this effect. And the linear effect, it should be noted that the MU radar data in the case is preliminary data, and the RCS may not be correct. In the future, I plan to derive and adapt the equation of relationship between RCS and magnitude separately for Gemini's and sporadic meteors. Next, I'll talk about MU radar and Tomo-e Gozen and spectroscopy results. Simultaneous meteor observation using 3 instruments are currently under analysis, so only the result of simultaneous Tomo-e Gozen and spectroscopy observation are shown. Simultaneous observations of Tomo-e Gozen and spectroscopic observations show that the two events are simultaneous in time. This is a triangle diagram I discussed earlier. The further away from the vertex of sodium, it is less sodium. Then this meteor spectrum is a spectrograph of the meteor here. You can see that the intensity of sodium is small. Finally, we would like to know the trend of meteor observed simultaneously by comparing the composition obtained by spectroscopic observation with the RCS obtained by MU radar. Thank you.